Welcome to this presentation called CAD to BIM for MEP. In this presentation, we will explore the transition from traditional CAD-based workflows to intelligent BIM processes tailored for MEP professionals. During this presentation, we will discuss about the main challenges the industry is facing and how BIM can help us to overcome them. You will discover the key capabilities of system analysis in Revit and how it empowers engineers to simulate and optimize building systems earlier in the design process. We'll walk through practical workflows and best practices for transitioning to BIM, highlighting how to improve design accuracy, energy performance, and model coordination. The AEC industry is undergoing a profound transformation. Sustainability is now a priority, driving demand for greener, more efficient buildings. Projects are also becoming more complex, with tighter schedules and more moving parts. Regulations and zoning laws are stricter than ever, adding layers of approval and compliance. And economic pressures, from rising costs to labor shortages, are forcing teams to do more with less. In this shifting landscape, innovation isn't a luxury, it is a necessity. But why MEP is so important in the AEC industry? MEP systems are the backbone of any modern building. They are not just essential to how a building functions, they are central to how it's built and how it performs over time. MEP systems account for 40% of construction spending and 30% of capital cost in a typical office building. That's nearly a third of the initial investment, right from the start. More than half of all construction service providers specialize in MEP trades, showing just how skilled and vital these roles are. And once the building is up and running, 40 to 60% of its energy use comes from MEP systems. That's where smart design makes a difference, lowering energy use and cutting operational costs. Even more striking, 75% of buildings' operational costs in the first decade are tied to MEP. In short, MEP systems don't just make buildings work, they make them efficient, sustainable, and cost effective. They are not an afterthought, they are at the heart of the entire construction lifecycle. In the MEP industry, every role has unique needs. On one side, within engineering service providers, we can find engineers that need to ensure system performance and compliance with precise design tools. Designers create detailed models focusing on accuracy and building codes. Estimators calculate cost using up-to-date databases and tools. On the other side, coming to the construction and the manufacturing, we can find detailers that create fabrication and installation drawings with advanced software. Fabricators build components based on these drawings requiring precision, and installers execute the plans on site, relying on accurate instructions and tools. Each role plays a vital part, and the right tools make all the difference. For years, traditional design workflows have struggled to keep pace with the growing complexity of modern construction. Teams often work in isolation, processes are fragmented, communication is scattered, and collaboration is driven by static documents passed back and forth. Design decisions are buried in spreadsheets, revisions multiply, automation is limited, and the sheer volume of details become overwhelming. With the rise of AI and building information modeling, a new path is emerging, smarter, faster, and more connected. AI helps automate repetitive tasks, flag issues early, and support better decisions. BIM brings all disciplines into a shared digital environment, integrating models, data, and workflows in real time. Together, they transform how we design, collaborate, and build, streamlining complexity into clarity. In a world full of changes, AI and BIM offer more than just tools. They offer a new way forward. Learn how MEP firms are adopting BIM processes to produce optimized, coordinated designs faster. Working in a BIM process gives MEP projects teams insights into design and constructability to improve accuracy, reduce and resolve clashes, and optimize building systems design. Using BIM, MEP engineers can make better decisions earlier to optimize designs, reduce risks, and improve accuracy and constructability. An MEP system engineer starts with the architectural model and creates Revit energy analytical model and runs the analysis to different levels of models spanning concepts to a detailed design stage. From here, the designer utilizes the BIM-based energy model and the results to design the system in Revit and continuously communicate with the project engineer as the design evolves. Let's now see the power of the system analysis in Revit.
Okay, so let me continue by introducing system analysis. System analysis is a suite of simulation and analysis tools fully integrated into Revit. Imagine this when you're working on a HVAC design, and before you even start drawing a single duct or pipe, you want to understand what the building really needs. So how much heating or cooling is required, where does the air need to go, is the envelope efficient enough? So system analysis helps us answer these questions. It simulates building performance in real time so you can make smart decisions about system sizing, zoning, and layout before getting into detailed design. It's all about designing smarter, not by uh, guesswork, but based on the data. Now that we have seen what system analysis is, let's look into why it's so valuable in design process. One of the key benefits is whole building energy analysis. This allows us to understand the total expected energy used across the building, even in early design phases. We can also run load calculations to determine exactly how much heating or cooling each zone requires. Instead of relying on assumption, we are using actual geometry, occupancy, and material data. The tool lets us simulate airflow and thermal comfort as well, so we can check if the ventilation works well and occupants will feel comfortable. And by connecting to Autodesk Inside, we get access to cloud-based simulations and detailed dashboards. Inside is a cloud-based analysis tool that works seamlessly with Revit. Uh, so if you want to go deeper, we simply send the model into Inside, and we don't need any extra software or powerful hardware. All heavy computations are done in a cloud. Inside provides us also some clear dashboards and visualizations for energy use, daylight, thermal comfort, and carbon footprint. So again, these helps us compare HVAC system options, evaluate maybe some renewable energy strategies, make informed design decisions. And because it outputs are easy to understand, because the outputs are easy to understand, even for non-technical stakeholders, it improves communication across the whole project team. So let me walk you through the typical workflow for system analysis in Revit. First, we define the building model. This includes geometry, room spaces, zones. Next, we configure system types and parameters, for example, HVAC system type, supply and return settings, or design conditions. And then we run load calculations and energy simulation directly in Revit. These calculations help us understand, just like I said, that heating and cooling needs per zone. And once the results are generated, we can review them and optimize the design. Maybe we adjust zoning, insulation, or ventilation strategies. So it starts, of course, with the building, with the correct BIM model in Revit that includes rooms, zones, wall types, windows, etc. And from that, we can generate analytical model. This analytical model is just simplifies, let's say, version of the building geometry optimized for simulation. The first thing users need to define the project location. This allows Revit and Insight to pull the right weather and climate data from the cloud. So these files include hourly temperatures, solar radiation, humidity, and more, all needed for accurate energy simulation. So we should set these, let's say, in the first steps before we create analytical spaces or run any calculations. After setting the climate data, we move to defining energy settings for the building and spaces. Spaces are analytical, let's say, volumes used in MEP workflows. They represent the actual air volumes of rooms and are required for system analysis, load calculation, and energy simulation. So once they are placed, we can assign the right space types and define properties like some internal loads, ventilation rates, maybe some lighting schedules, and more. These parameters are key for accurate simulation results. And once everything is defined, we generate the analytical, or we can generate the analytical model. Analytical model includes both analytical surfaces such as walls, windows, floors, and the analytical spaces. And so finally, we can just check the results in the schedule view, where we can review some surface areas, maybe some window counts, room volumes, or individual space loads. So these data is the foundation for the further calculations and optimization. As you just saw, analytical spaces represent the internal volumes of the building, but these spaces are surrounded by walls, floors, roofs, and windows, and those have material properties that influence energy performance. So in Revit, we can, of course, define thermal properties at different levels, computer types, schematic types, or real detailed elements. So each element has parameters like U values, thermal mass, or maybe some conductivity, which are automatically read and used in the simulation. So these settings help us calculate how heat transfer through the envelope. So we are using these data from a model, which is of course essential for accurate energy and load analysis. Once we have an analytical spaces and materials defined, we can move to assigning, for instance, HVAC systems. This is a critical step because the type of system we assign has a big impact for energy use, comfort, and some simulation result. And in Revit system analysis, we work with the four, let's say, key components. We have system zones, zones, equipment, air systems, and water loops. So these definitions allows Revit to simulate realistic system behavior, like how heat is delivered, what equipment is used, and how it responds to load. So we can also add some custom parameters for more detailed control, or bring in OpenStudio measures for advanced performance data. And this structure ensures that the analysis results our real design intent and not just the generic estimate. And now we can run the system analysis and get the results on the building's performance. Once we run the analysis, we get a detailed report directly in the model environment. So we can look at the results for each zone, like here where we see a zone load summary. It gives us key values such as peak temperature, airflow requirements, and cooling or heating loads. Then broken down by envelope and internal gains. Then we can go one level deeper and check, for instance, system load summary. This shows how the entire HVAC system performs, aggregating all zones together. So it's very helpful for system sizing and capacity checks. And there are also some visual charts. For example, we see which components contribute most to the cooling load. This gives us a better understanding for where the energy demand comes from and how we might reduce it. And these results gives us a full year overview of how the building performs for energy consumption to occupant comfort. So here we can see different visualization by charts for total energy use and breakdown by source, like heating, cooling, lighting, maybe some equipment. So this again helps us understand where most of energy goes. And we can also view some monthly trends, like this bar chart showing cooling peak demands across the year. There are also a tabular view with a precise monthly data for each system, so we can verify annual performance metrics such as energy use, intensity, or electricity usage. So far we looked mostly at energy and comfort, but if you want to go deeper, simulate energy use, carbon footprint, or daylight, we can send the model to Insight, and the cloud takes care of all heavy calculations, and we get back easy to read dashboards and visuals. So as we can see here on the left, we have a 3D model. On the right, we can see dashboards that break down the embodied and operational carbon. This is that is emissions from materials and from energy used during the building's lifetime. So this helps us make smarter, let's say, material choices early in the design. And we can also analyze by material type, construction, or area, which gives us a full picture of environment and environmental impact. One powerful feature is also ability to create custom metrics, like we can create that calculates operational carbon after some panels are installed. We can create our own dashboards for example, a study focusing only for renewable energy. So we define some panel size, and immediately we can see how much carbon we can save and how it affects the overall building performance. So it's a flexible and a visual way to connect sustainability goals with the actual design decisions. To sum it up, system analysis gives us the tools we need to design smarter. We can make decisions early when they are still easy and cheap to change. And we optimize our systems, reduce waste, and design for real comfort and efficiency. And because the results are visual and easy to understand, we can align better with clients, consultants, and internal teams. So this is how we move toward better, more sustainable buildings, not just technically, but also practically.
After analyzing the model and gaining insights from simulations calculations, you can move on to modeling the systems. In this step, we will be creating the coordination model. The coordination model helps assess how the MEP design integrates with other disciplines, addressing and solving complex building nodes in advance, and will allow us to generate the technical documentation needed for the next phases of the project. Starting with the architectural model as a reference, we will generate the MEP model by placing the components and modeling the distribution lines. Use schedules to verify system values and confirm the technical requirements. Finally, we will produce the technical documentation for the field or other stakeholders. Looking into the detail of the MEP system modeling, we start by placing equipment and terminals to define the system endpoints. Then we generate the initial layout using automation and customizing it as needed. As we detail the system, we can adjust the hierarchy and use Revit automatic ducts or pipe sizing to ensure the model's accuracy. Finally, we get to a spatial, coordinated, and developed model that we will then share for different uses, which could take actually two iterations of the design process until we get to the final project design. Let's take a look at how components works in a BIM model. In Revit, MEP systems are represented by components specific to each discipline. These elements help create both the physical and the analytical models for the MEP systems. Using Revit's modeling tools, we can digitally construct all building services for the project, and after modeling, simulations and calculations can be run within Revit or using external programs. As we advance through each phase, we define and place system components. When air terminals are added, for example, their data helps calculate air loads and ensures correct sizing. This also verifies the right mechanical equipment for each system. Components can be pulled from vendor BIM libraries or can be customized for standard use across projects. Unlike CAD blocks, these are Revit families with rich associated data. Ductwork and pipework connect terminals, like air terminals or plumbing fixtures, to the mechanical and plumbing equipment. You can draw ducts and pipes using routing commands from connectors in the MEP components. Connectors are key for adding intelligence to components, enabling load calculations within the project. Revit tracks load information for spaces, updating as devices and equipment are placed. These loads can be viewed in space properties and schedules. In Revit, elements aren't just geometries, they are actually intelligent families containing key data through parameters. Parameters define, control, and display important information about building components. They make Revit models parametric, allowing elements to adapt based on these parameters. Unlike simple 2D CAD blocks, families store data that can be pulled into schedules or documentation, simplifying tasks like quantity takeoffs, minimizing errors, and aiding the creation of a digital twin. With the architectural model linked to the MEP BIM model, you access the same consistent data as architects. Place 3D views, sections, and elevations to support your layout. To place air terminals, go to the System tab, select Air Terminal, and choose a type. Use the spacebar to rotate and the midpoint snaps to center the devices. Set the elevations in the Properties palette. Rooms with the same airflow can be grouped and adjusted in the Options bar or Properties. Mechanical equipment is placed similarly by selecting it under the System tab and using the Type selector. Once terminals and equipment are in place, start duct modeling by routing from air terminal connectors. Snaps and guides align components, and fittings are added automatically. You can split ducts, change sizes, and Revit will adjust fittings accordingly. To hide linked models, use the visibility graphics in 3D views. Adjust mechanical equipment elevation for vertical routing, and you can use cap open ends to close the ducts. The duct tool under System tabs allows you to customize ductworks with fittings added automatically. Switch to sections views at any time. No extra modeling needed. Sections show all content and act like plan views. Once connected, moving any part of the duct system adjusts all linked components, showcasing the power of BIM over CAD. Next, let's talk about spaces in the system browser. Spaces are used in MEP disciplines to analyze volumes and should be placed throughout the model, including areas like plenums. They contain parameters that store information about the areas they occupy. The system browsers shows a hierarchical list of all components in the project, organized by model systems, zones, or analytical systems. It's also useful for identifying components not assigned to a system. Revit lets you model large connected building services with powerful analytical and parametric tools that enables data flows across the network while manipulating your MEP model. Now, let's watch a short video on the system browser. The system browser displays components for each discipline, and you can filter by discipline. For example, mechanical show duct systems in your project. When you select a component in the system browser, it highlights in the drawing area since both are linked. Selecting an item from the duct network allows you to use the duct system tab and select the equipment tool. Using mechanical equipment creates a folder for the supplier duct system with terminals at the end of the hierarchy. The Properties palette displays system details such as system name, and you can customize this view with column settings to show data like pressure drops or static pressure. By organizing components into logical systems rather than leaving everything on the default system, Data flows through the model, aiding analysis like pressure drops and calculations. Let's move on to the automatically generated duct layouts. Use the Generate Layout tool to create duct or pipings, layouts, and connect system components, even across multiple levels. Revit will generate solutions, and after selecting a solution, you can easily edit layout to customize it by repositioning or combining layout lines. Go to the Systems tab and click the Mechanical Setting Launcher to access duct conversion settings. Here, you can set parameters like elevation and duct type for main and branch segments. In this example, supply air uses meter elbows with tabs at 9 feet elevation with no flex duct. Select components in the drawing, then use the Duct tool from the Create System panel. This opens the Create Duct System dialog where you can rename the system before it's created. Next, use the Generate Layout tool on the ribbon. Revit will propose layout solutions, network, perimeter, or intersections, each offering multiple options. Use arrows buttons to browse through the solutions. To customize one, select Edit Layout to adjust or combine layout lines. You can revisit and edit your custom layouts anytime or overwrite it with a new one. Using Revit's BIM tool to generate duct layouts streamlines design and improves system performance. Revit offers standard methods for calculating duct and pipe pressure drop, with third-party add-ins available for additional calculations. Revit automatically calculates sizing and selects ductwork for systems. You can choose a dynamic sizing method through the duct sizing dialog, applying to each section or entire systems. Duct sizes can also be constrained using options from the constraint list. Now let's watch a short video on duct sizing. Select the ductwork to size in the drawing area. From the analysis ribbon, choose the duct sizing tool to open the duct sizing dialog. Pick a sizing method, velocity, friction, equal friction, or static regain. From the dropdown, you can constrain duct sizes by setting limits in the constraints list. Revit calculates pressure losses based on duct geometry, roughness, air density, and viscosity, requiring a connected duct system with valid airflow. Airflow for equipment is calculated as aggregate of downstream components. Revit will size ducts based on the parameters you've set, making adjustment easy when changes occur. A major advantage of BIM software like Autodesk Revit is the ability to automatically obtain quantities directly from the model, streamlining estimation and planning with real-time accurate data. Unlike traditional CAD workflows, which rely on manual quantity calculations and are prone to errors, Revit updates quantities and materials takeoffs automatically as you design. This reduces human error and ensures precise current data. This automation saves time, improves project estimates, and allows teams to focus on creativity and problem solving, ultimately leading to cost savings and better outcomes for clients. In short, adopting BIM tools like Revit enhances productivity, accuracy, and collaboration, enabling teams to deliver projects more effectively. Every element in your system is data rich, thanks to parameter-driven logic. You can access and display this information using intelligent, customizable tags. These tags automatically update whenever changes are made to the associated elements. Because you have built a digital model, not just a 2D drawing, you can generate a wide range of views directly from it. From plan views with varying cut heights to highlight specific elements, to elevations and sections that clearly shows how your system interacts with the architectural and structural design. You can enhance your deliverables with technical details, schedules, and 3D views, making them more informative for teams in the field or other stakeholders. As your project evolves, there is no need to redraw. Any changes to the model are instantly reflected across all views, 2D, 3D, and in your schedules, ensuring consistency and saving valuable time.
Okay, and let's now look at how we can improve collaboration, especially for MEP coordination, and we will use for that some functionalities from our construction cloud. And I'd like to show you how all disciplines, architecture, structure, MEP, can work in one shared environment. One big part of every coordination is detecting clashes. So let's take a closer look at this topic right now. Automatic clash detection identifies conflicts between models before they cause costly issues on a site. Before we even start build a building, it's really important to find and fix any clashes or problems in the design. And with this model coordination from our construction cloud platform can really helps us with that. It automatically checks models stored in the cloud and shows us where the issues are. In the settings, we can pick one or more folders saved in the cloud and turn them into what we call coordination spaces. As soon as we add modules there, the system checks them and find any clashes. So we can create a different spaces for different parts of the project or different teams depending on what we need. And the class results are shown in a simple metrics, so it's easy to see where the problems are, group them, or decide what to fix first. So teams don't have to wait for the next coordination meeting. They can react right away and keep things moving. And we can also quickly create issues straight from the clashes and assign them to the right people, so everyone knows what to do, what needs to be fixed. And this really helps the whole team spot, track, and fix module conflicts early before they become bigger problems later. Once we detect the clashes, we need an easy way to manage them and make sure nothing gets forgotten, and that's where issues come in. And as shown in previous video, model coordination enables us to create, assign, and track coordination issues directly from clashes between modules, helping to ensure accountability and resolution. And we can also use a Revit issues add-in, which allows us to view and respond to issues created in model coordination directly within the Revit project environment. So once you have reviewed the issue in Revit, you can update the status accordingly in the issues panel. Updates to issues are immediately reflected in a cloud. And similarly, the coordination issues for Autodesk Navisworks add-in enables team members to open models in Navisworks directly from coordination spaces created in cloud. Team members can view issues by selecting the Manage Issues icon on the right ribbon, and issues created either in the cloud or in Navisworks will appear with a pin, a reference image, and issue information in the right hand pane. So in the same way as in model coordination, Navisworks Manage enables you to review individual clashes in context to help find and resolve conflicts. Using this add-in, Navisworks users can easily create and share issues across the project team, greatly simplifying communication during the coordination stage of a project. And once an issue has been addressed or created in Navisworks, it will be visible in Revit, in model coordination in the cloud. So the ability to seamlessly share issues between Revit, Navisworks, construction cloud enables the best features of these products to be used together during the coordination stage, providing a single source of truth for entire project team.
With this, we are finishing our presentation about CAD to BIM for MEP. If you have any doubts about the content of the presentation, don't hesitate to contact the technical sales team or your customer support for any clarifications. Thanks for watching, and we hope you enjoyed the presentation.